In many modern building complexes, the problem of disorientation is acute. People have no idea where they are, and they experience considerable mental stress as a result. Greetings, Internet scholars. This is your Jesse Stiles. Welcome to a very special episode of Twisted Signals. Today we are going to learn about some fundamental properties of signals. If we're going to talk about signal processing, we need to understand the basic terms that we use to describe signals. So let's start off by talking about periodicity. So a signal is periodic if it repeats itself. So here we have an oscillator. The oscillator is oscillating and it is repeating itself. A periodic audio signal is going to sound to us like it has a fixed pitch because it is repeating itself at a certain time period. And by changing the frequency, we are changing how often that signal repeats itself. I've got a few different types of oscillators up here. These all produce different types of waveforms. They have slightly different sound qualities. So if you are a musician, you might say these three different signals have different types of timbres. Some of them sound brighter than the other ones. But all three of these signals have the same periodicity. They have the same frequency. They sound as if they are the same note. So all three are periodic. My fourth signal here, you can see by looking at it in our scope here that this signal is completely random. It is not repeating itself. This is known as noise. So noise is a fully random signal. It is never repeating. And it does not sound to us, when we consider this as an audio signal, it doesn't sound to us as if it has any fixed pitch. It's just like completely random frequencies that are constantly changing. So that's a fundamental property of signals, whether or not they are periodic. As we've seen, a periodic signals can have different types of shapes. So here we have an example of something that is a complex waveform. This is a waveform. It is, as you can see, periodic. It is repeating itself, but it has this complex structure. If we look at the red version of this, it has this complex waveform because it's actually made up of three different sinusoids that are added together. Still, it's repeating itself and it sounds like it has this fixed pitch. Sidebar, for those of you who are musicians, this is sort of a curious phenomenon here. The note that we're hearing is different. It has a different frequency than the frequency of these three oscillators. So we have an oscillator that is repeating itself 202 times per second, another one that is 303 cycles per second, and 404. You put them together and you hear this note, and that note is actually a different frequency. So it should be this one. Yeah, that's the note we were hearing. So we had this kind of like phantom fundamental frequency, which is because all three of these were multiples of the same kind of base frequency. Our brain put that frequency in there for us. So there's a fun party trick you can try to impress your friends. Let's look at some other fundamental properties. Here, this patch, we've got A nice sinusoidal oscillator, and it is repeating itself at this frequency that I've specified with this argument. So this is 100.1 cycles per second, and we could change the frequency of this oscillator using this number box. So some of these frequencies are going to look a little bit more stable on my screen, which just has to do with the kind of refresh rate of the screen itself. It doesn't have anything to do with like the specific frequency. Okay, so yeah, there's a nice image of our audio signal, which is now repeating itself 302.3 times per second. So that's the frequency of this audio signal, which is related to the time period in which it repeats itself. So that relationship is that the frequency is 1 divided by the time period. Another super fundamental aspect of signals is the amplitude. And so that's going to be the displacement of this signal off of the x-axis. And in the world of audio signal, amplitude is going to be related to the perceived loudness of this sound. And the frequency, the repetition rate, is going to be related to the perceived pitch of that sound. What we're looking at here, by the way, this is frequently referred to as an oscilloscope, and it's a way to visualize a signal in the time domain. So that means we're looking at the signal over time. So the x-axis here kind of represents time. A third super fundamental aspect of signals would be the phase of a signal that is repeating itself. So here we've got two different signals. These signals have the same frequency, they have the same amplitude, but they are out of phase with one another. So when one of these signals has a high amplitude, the other one has a low amplitude. So phase refers to where this repeating waveform is in its repetition cycle. So these two signals are identical in every way except for phase. This, incidentally, is how many forms of noise canceling work. If you take an audio signal, so let's just do a demonstration of this. Let's make an audio signal like this. That is creating sound that we can hear. Now let's add something to this audio signal using plus tilde. So right now it's adding nothing to it, so we just hear the original audio signal. If we take the same audio signal and let's just multiply it by -1, multiplying by -1, let's just look at a scope here. There's our audio signal. Multiplying by -1 takes the amplitude and inverts it, so when one is high, the other is low. Let's add them together and see what we hear. Nothing. So these two signals cancel each other out. Let's just make a third oscilloscope and look at the output. It's 0. So because the two signals are out of phase, they add up to nothing. That's the basic idea behind a lot of noise canceling headphones, is you take the sound that's coming at your headphones and you invert the phase of it and add it together, and then it sums up to 0 and you get silence. Cool. So let's look at some slides, some sweet, sweet slides. Great. So here are a couple oscillating waveforms. We've got a cosine and a sine. So these are two mathematical functions that describe the displacement of a point as it moves along a unit circle. The unit circle is the circle whose radius has a value of 1. The cosine function shows us the displacement of that point along the x-axis, and the sine function shows us the displacement on the y-axis as this circle, as the point moves around and around on this circle. So these are two functions that give us this sinusoidal function, and these are super common when we're talking about like describing signals and creating complex signals. These are the building blocks. Next slide. So let's talk about this unit circle because it'll help us understand some units that we use a lot. The radius is 1. So the distance that we have to move to go all the way around this circle is going to be, there's 1 radian. And if we move 2 and then 3 and then 3.14 radians takes us halfway around the circle, and that's pi. And then 2 pi would take us all the way around the unit circle. So this is the function that describes any sinusoid. This would be like the difference equation. So for our output y at any given time, we can describe it this way. We've got like a sine function to give us that sinusoidal output. 2 pi multiplied by the frequency, and then time is going to give us the sinusoidal output, where f is our frequency scalar. So if f has a higher value, we're going to be multiplying the repetition rate of that signal. We can add some offset to it, and that will give us phase. So 2 pi multiplied by frequency, and then our time value, and then offset by phase. We run that through our sine function. That gives us this displacement that describes the sinusoidal waveform. We take the output and then we scale it by a, and a would be changing the amplitude of that signal. Let's talk about sampling. So sampling is a term that you hear a lot in music production. You talk about sampling a record or sampling a piece of recording. This refers back to the original digital sound recorders that we use when we're producing certain forms of electronic music. Sampling is where we convert a signal from continuous time or continuous space into discrete time or discrete space. So in the world of computers, all signals are discrete. Everything is ones and zeros, and we have to look at time at discrete points in time. There's no such thing as continuous time in the world of a digital system. So for us to record a sound in the real world using a computer, we have to measure it at discrete points in time, and that measurement process is called sampling. So when we convert a signal from continuous time to discrete time, we are sampling it at this rate, which is going to be our sampling rate. So here, that rate that describes the sample rate is written as t. So we say x of n in brackets, that's going to be time, but in the world of a discrete signal, is x in continuous time sampled at this sampling rate. So this is another convention that you'll see in signal processing, is units that are in discrete time or in discrete space are going to be written in brackets, and then things in continuous time or continuous space will be written in parentheses. So continuous time versus discrete time. Continuous time, we've got x of t in parentheses, and you can look at the value of this signal anywhere you want to in time. It's this completely fluid curve. But when we sample it with a computer, we convert it into x of n, where that's going to be discrete measurements at our sampling rate, and we can only look at the values at those moments where we've sampled it. So here is my drawing of what goes into making a sound recording in a digital system. You start off with some acoustic sound. So let's say we have a trumpet. The trumpet is displacing air, and that air, it creates this pressure wave that moves through the room, and we use a microphone to measure that pressure wave to create a signal based on the pressure wave. So a microphone is a form of a transducer. A transducer is a device that converts one form of energy into another form of energy. So a microphone converts acoustic energy into electrical energy. And it does that using this clever little system that I've diagrammed right here. A microphone, if you were to cut it in half and look at the cross section, you would see a diaphragm. So like a piece of paper, for example, that is suspended. Excuse me. And on the back of this diaphragm would be a copper coil. And the diaphragm is suspended in front of a magnet. And maybe you remember this trick from your physics class, but if we can move a piece of copper back and forth in front of a magnet, it's going to create a differential current. So you're going to create a current that is increasing or decreasing based on the amount of magnetization that comes from that copper coil. So the acoustic pressure wave hits that diaphragm and it causes it to move back and forth in front of that magnet, and that creates this varying current. And so the level of current inside this signal is analogous to the acoustic signal. So it has a similar shape. Because it is analogous to that original signal, it is an analog signal. It's not an exact copy of the acoustic signal, but it has a similar shape. And both of these signals exist in continuous time. We could think about the level of that pressure wave at any instant in time. You could go back and forth as much as you like. And similarly, if we look at the electrical signal coming out of this microphone, this is in continuous time. And these two signals are related to each other with this analogous relationship because of the transducer. If we want to get this signal into a computer, we're going to run it through this device called an ADC. This is our analog to digital converter. And what the analog to digital converter does is sampling. So it measures the level of this electrical signal at discrete points in time, and the result is this lollipop train of values, which is our digital audio signal. So this train of values is the digital version of the analog signal. Conversely, if you want to take sounds that are inside of your computer and play them through loudspeakers or through headphones, you have to do the opposite thing. So you have your digital signal, which is just a bunch of measurements of amplitudes throughout time at these discrete moments. And we have to convert it into an analog signal. So to do this, we use a DAC, which is our digital to analog converter, and it converts it into this fluctuating current. We can take our fluctuating current and we can amplify it using an amplifier and then hook it up to a loudspeaker or hook it up to headphones. And a loudspeaker and headphones, these are also transducers. They convert one form of energy to another. In this case, they're doing the opposite thing of the microphone. They're converting current into acoustic energy. And interestingly, if you were to slice a loudspeaker in half, you'd see the same thing as a microphone. Again, you just have a diaphragm with a copper coil suspended in front of a magnet. In this case, the varying current is causing the magnet to become differentially magnetized, and that causes the diaphragm to move backwards and forwards in front of this magnet according to the electrical level of this current, and that creates the acoustic pressure wave that results in sound. So loudspeakers and microphones are actually the same technology. And in fact, you can use them interchangeably if you have the right kinds of adapters. So if you look at sort of studio recording hacks through history, you'll see examples of people using loudspeakers as microphones. Like in the Motown recording studios in Detroit, they famously would use large loudspeakers as microphones to record kick drums because they picked up bass better than any microphone could. And that's why those Motown records had such good sounding kick drums, is because of this amazing hack that those engineers came up with. Image signals. Image signals in computers are also sampled, but an image has values that vary over space as opposed to time. So when we take a digital photograph of something in the real world, we're also sampling color, but we're not sampling it over time, we're sampling it over continuous space. So when you take a picture of something like with your phone has a built-in digital camera, you're gonna get an image that has a certain size. So like, let's say it's 4,000 by 6,000 pixels. It's measuring color values at this discrete sampling rate over the area of that photograph. So if we were going to sample this triangle at a certain sampling rate, which is spatial, you'd get an output like this. So this would be a kind of, let's say, low resolution representation of this triangle. Here is a block diagram that represents a digital signal processing system. We have some signal that exists in continuous time, and we convert it to a digital signal, which gives us x of n. So this is x of n in discrete time. And then we've got our discrete time processing system that gives us y of n. And then if we want to convert it back into an analog signal, we do it through a D to A converter, and then we get y of t. We're back in continuous time. And this could be time or space. Let's talk about sampling rates. We've talked about the frequency of signals, which refers to how frequently it repeats itself in time. So at the top of my graph here, I've got this signal that repeats itself twice per second. So this has this repetition rate of 2 cycles per second, which means hertz, 2 hertz. Hertz is the unit that refers to repetitions per second. So if we wanted to sample this signal, let's look at sampling it at a sample rate, which is twice as fast. So let's say our sample rate is 4 hertz. That means we're going to take measurements 4 times per second. So we're taking snapshots 1, 2, 3, 4. 1, 2, 3, 4. And what we get is this lollipop train this is the digital version of this signal. We could do whatever we want to it, and if we convert it back into an analog signal, we would get this. We'd connect the dots between our measurements, and we successfully reconstruct this signal. The frequency is preserved. So sampling this 2 hertz signal at a sample rate of 4 hertz, this works. We can accurately represent the frequency of this signal. If we sampled it at a sampling rate that was less than double that frequency, however, we would run into problems. So here is the same 2 hertz signal, but this time we're going to sample it using a sampling rate of 3 hertz. So we would measure it 1, 2, 3 times per second. 1, 2, 3, and we get our lollipop train. And when we try to convert it back into an analog signal, we connect the dots, the frequency that results is this. You can see this is different than the original audio signal. So this is an error. This is referred to as aliasing. This is the wrong frequency. So when our sample rate is less than double the frequencies that we want to work with, we are going to get these errors known as aliases. Okay, so let's look at the frequencies we would work with in audio signals. The range of human hearing in terms of frequencies is as low as 20 cycles per second and as high as 20,000 cycles per second. Those would all be audible frequencies. So here's a patch you can use to test your hearing. Let's start audio and turn up the volume. And right now we hear a tone at 440 cycles per second, but here we can change the frequency. So if your hearing is really good, maybe you can hear this very high frequency audio signal. This is 17 kilohertz or 17,000 cycles per second. I'm going to turn it up again. I can kind of still hear that. One of the things that happens to you as you get older is you lose the ability to hear high frequency sounds. So young people can actually hear high frequency things that older people cannot hear. So in fact, the process of being alive is sort of like having a low pass filter slowly applied to your life. As you get older, you hear less and less high frequencies. So you can use this max patch to test your age. If you can hear audio signals at frequencies above 17 kilohertz, you might be a young person, or you just have good hearing. You haven't damaged your hearing too much. So let's look at the sample rate that my computer is running at. If you go to your options and you look at your audio status, you'll find this window, which shows you this is the sampling rate of the sound card that we're going to be using in Max. So you can see my sampling rate is 44,100 samples per second. This is a very common sampling rate. And this sampling rate relates to that range of frequencies that describes human hearing. If the highest frequency that a human being can hear is 20,000 cycles per second, a sampling rate that is double that highest frequency is going to be able to accurately represent the entire range of frequencies that constitute human hearing. So 44,100 samples per second would allow us to accurately represent signals that go up to 1/2 of that sampling rate. So that would be 22,050 cycles per second. And that covers the entire range of human hearing. So this sampling rate is going to be a good one for digital audio. It's going to let us accurately represent all of the frequencies that human beings can hear. There are other animals in the world that have an even wider range of hearing in terms of frequencies. So like cats and dogs can hear frequencies that are much, much higher than 20,000 cycles per second. So if we were making a sound system for a cat, our sampling rate would in fact need to be much higher. And if you have a fancy sound card, like I'm using a fancy sound card, you can actually click on this sampling rate and you can use much higher sampling rates. So using these higher sampling rates would allow you to accurately represent signals where the frequency is much, much higher than the range of human hearing. So if you're producing records for cats and dogs, I would strongly encourage you to use these higher sampling rates. If you're working with humans mostly, I think this sampling rate is perfectly good. Just use this. There's some confusion about this. Like in the world of audio files, you'll frequently people describing their sampling rate as if bigger is better. But really, a bigger sampling rate all it's going to do is like use more computational resources to represent signals that you can't even hear. And in fact, might cause your sound system to behave weirdly and create distortion because your amplifier and speakers are not designed to produce these frequencies outside of the range of human hearing. So you can use these higher sampling rates if you want to, but you won't be able to hear the results. There's no benefits for humans. Plus, like maybe you'll actually create distortion by playing it through loudspeakers and amplifiers that aren't really meant to use those frequencies. However, if you are working on records for cats and dogs, good choice. So, you might wonder like why these sampling rates are even available on pro equipment. There are some edge cases where this is useful. Like, for example, if you wanted to take a sound recording and slow it down a lot, like repitch it a lot, if you were doing like special effects for a movie, that's a very common technique, is like record a sound and then change the speed of that sound radically. Using this higher sampling rate would give you some flexibility when you want to like resample it to change the pitch. So there might be some reasons to do it, but most of the time, that's a nice sampling rate. Let's just leave it right there. Let's look at what happens when our sampling rate is some suboptimal value. So when the sampling rate is below this range, where it should be double the highest frequency we want to hear, we're going to introduce these errors known as aliasing. So let's listen to some aliasing. You can intentionally create aliasing using this max object, degrade tilde. This is going to reduce the sampling rate of an audio signal. So we're going to give it a floating point number where 1 would be the original sampling rate of our sound card, and then anything less than 1 is going to reduce the effective sampling rate to some lower value. So let's just play this drum sound and change the sample rate. So you can hear, you start to get these like actually interesting sounding artifacts when you intentionally introduce aliasing. So this is actually an effect that people like to play with creatively. We could put some different sounds in here by adding an open message, and I've got our good friend Alvin Lucier here. Let's listen to Mr.
I
Lucier.
am sitting in a room different from the one you are in now. I am recording the sound of my
So by intentionally reducing the sampling rate of this audio signal, we're creating aliasing, and it actually gives us some interesting musical effects. When we understand what's going on, we can use this in a creative way. So one of the first places where I heard this technique used, at least in the world of somewhat more popular music, was a Bjork piece called Undo from her album Vespertine. If you listen closely in the last 45 seconds of that song, you'll hear this repeating motif played on, I think it's a harp, and you'll hear the sampling rate on that harp sound is getting lower and lower and lower. And as it's getting lower, you can hear these aliasing frequencies that begin to are introduced into the piece, and it's actually very beautiful. So I'll put a link to that piece in the description of this video if you want to listen to that. Let's look at this sampling rate of an image. So we've given you some examples that look at the sampling rate of sounds. Let's change the sampling rate of some digital images. Is this working? Okay, great. This is a test signal. It's a digital image, and this is called like an optical checkerboard. And as you look at this image, you can see that there are many different frequencies inside of this image signal. So if you look at it from top to bottom, you'll see that the signal is changing from a high brightness to a low brightness, and it's doing this repeatedly throughout, and there are different repetition rates. So here we have a variety of frequencies represented in terms of how often the brightness changes as we move from the top to the bottom, and also from left to right. We have the image signal is changing brightness from high values of brightness to low values of brightness as we go from left to right, and it's doing it in this repetitious way where there are different repetition rates inside of this image signal. But here the repetition rate, these are not sounds, these are brightness values across space as opposed to loudness values across time. So the sampling rate of this image signal refers to how often we measure these color values or these brightness values as we move across it in space. So I can change the sampling rate of this image using my mouse. I'm moving my mouse to reduce the sampling rate. And you can see I'm beginning to introduce aliasing into this image signal. You're seeing all these new frequencies in the image signal that are not there in the original. So these are phantom frequencies inside the image. So this is aliasing. It's just spatial aliasing. And we're creating new frequencies by using bad sampling rates to measure the brightness of this image horizontally and vertically. Let's look at another image. Next image, please. Okay, yeah. So here is another image that has it has frequencies vertically and horizontally. These bricks are changing their color values in a repetitious way as you look at the image from top to bottom and from left to right. So you have these different repetition rates within the image signal. And if we have a nice high sampling rate, it looks normal. That looks like a normal brick building. But if I, again, introduce the sampling rate or reduce the sampling rate, you're going to begin to see these other frequencies appear inside of the image. So you can see these kind of like wavy looking bands. These are new frequencies that did not exist inside the original signal. These are sometimes also called moire patterns. And they're kind of like, they look like they're swimming across the image as I change the spatial sampling rate of this image signal. And we can do the same thing to a video. So here's a clip from 2001. This signal also has some different frequencies in terms of how the colors repeat themselves across the image. You can see these like lines inside the floor. So if we reduce the sampling rate of this image signal, again, we can synthesize some new visual frequencies inside of this image that were not there in the original. You can see these like wavy curves that are not part of the original image. So those are all artifacts of the sampling rate, but in this case of a visual signal. Right. Thanks, friends. Finally, in a video signal, we have our sampling rate in terms of space. So that's going to be the resolution of the video. And we have the sample rate, which is how often we represent the image signal over time, which is like the frame rate. So if we change the frame rate of a video, let's find that same video from 2001. It's Dave, and Dave is jogging. So here is our source video, and the frame rate is nice and fast, but this metro here is giving us a different frame rate. So here are our sampling rate of the video signal is we're getting 1 frame every 300 milliseconds. And when we do that, it doesn't really look like a fluid continuous image anymore. It really looks like just a bunch of pictures presented one after the other. So we want to choose a good frame rate in order for our video to look like it's a continuous moving image. So here we're getting frames once every 22 milliseconds. So some common frame rates for videos are like 30 frames per second or 24 frames per second. Those are both frame rates you'll see a lot. Our metro, we specify the bangs in terms of the period. So how many milliseconds per frame. So if you want to convert frames per second into milliseconds per frame, you'd have to do some math. So for 30 frames per second, you would do this. So a time interval of 33.33 would give you 30 frames per second. A frame rate of 24 frames per second would be 41.6. So there's 24 frames per second for you. All right, Internet, thank you for joining me for another thrilling edition of Twisted Signals. I'll see you later. Peace.